Hi Professor, we're from Group Omega, and today we'll be analyzing about the change in gold price. And the methodology we used is, first of all, we collected the data, and then we processed it, and then we visualized it, continued with an ADF test, ACF analysis, PACF analysis, decomposition, and ARIMA modeling.
For time series plot, here are some key observations when looking at a time series plot. For trend, to see whether the trend is increasing or decreasing, or if it's stable. For seasonality, any repeating data. Volatility, any fluctuations. And structural breaks, if there are any shifts in the trend. Since the data starts at June and there are 52 weeks in each year, there are noticeable trends such as a decrease in 2022 and an increase in 2024 and 2025.
Next up, we're going to talk about the augmented Dickey-Fuller test. Now, this test is to know whether the data is stationary or non-stationary. And usually, data need a stationary value so that the data is predictable in a statistical sense. And here, the null hypothesis that it has a unit root, and the alternative hypothesis is there is no unit root. And from the test, we can see that the p-value is 0.999, which is more than 0.5 p-value. So we reject the null hypothesis, making the data non-stationary. Next up, we differentiate the data so that it becomes stationary. And this is the graph after differencing, and you can see that it has a very different graph.
Autocorrelation functions. Let's look at the autocorrelation function, or ACF. This tool measures how current values of a time series relate to their past value. In other words, whether today's value is influenced by previous day. On the left is the autocorrelation plot for the price variable. Each blue bars show correlation at different legs, with the red line marking the confidence interval. Bars outside the red line suggest statistically significant correlations, like at leg 1, meaning there may be short-term patterns in the data. In the center is the autocorrelation table, which give the ACF coefficients, TV value, and the de Box Q test. The smaller the p-value in the LBQ column, the more likely it is that autocorrelation exists. To sum up, if we see significant autocorrelation at lower legs, the data isn't purely random. This measure we might use past value to predict future ones, a key concept in the time series forecasting like ARIMA models.
Next, the partial autocorrelation function is a tool used in statistics and time series analysis. In simple words, it measures the direct relationship between the time series and its past values, removing the effects of values in between. For example, the ACF at leg 3 shows how much today is related to 3 days ago, after removing the influence of day 1 and day 2. So why is it useful? It helps find out which past values really matter in predicting the future. It is often used to decide how many past values to use in models like autoregressive models. In summary, autocorrelation is how related is a value to its previous values, including indirect effects. And the partial autocorrelation is how related is a value to a specific past values, after removing the influence of all the other values in between. For example, if you want to know if today's temperature depends directly on the temperature 3 days ago, but not just because yesterday and 2 days ago were similar, use PACF. In short, PACF shows the pure relationship between a value and its leg ignoring effects from the ones in between.
For the next slide, I'm going to talk about the decomposition analysis, definitions, and components. So what is decomposition analysis? It's basically a technique used to break down a time series into several distinct components to better understand the data's behavior over time. There are three underlying components. The first one is trend, the long-term progression or direction in the data. The second one is seasonality, regular repeating patterns or cycles at fixed time intervals. And the last one is residual, random variation or unexplained fluctuations. And now let's take a look on how the full time series decomposition value validates these insights while highlighting strong predictive performance. As we can see, there are two charts in this slide. The time series really exhibits a clear upward trend in the time series decomposition plot. Seasonal patterns acceptable forecast accuracy. While the model performs well overall, there are some residual structures such as room for refinement, potentially with more advanced modeling and including external variables. And next to it, there are the component analysis, which are divided between original data, detrended data, seasonality adjusted data, and seasonality adjusted and detrended data at one chart. So in the original data, we can see a strong declining trend with a pronounced cyclical fluctuations, which means there are a significant seasonality and noise. And in the detrended data, there are regular seasonal patterns with consistent amplitude, which means that it has predictable periodic behavior. And lastly, it has a steady downward trajectory after an initial highlight, which highlights the dominant role of seasonality in the raw data. For the next slide, there are seasonal analysis. This seasonal analysis has clear peaks and troughs with variations ranging from plus 200% to minus 200% with strong cyclical patterns, and the detrended data graph confirms the consistent seasonal cycles, and the residual graph with random scattering confirming the trend and seasonality were properly isolated. In the residual plots, as we can see, it might not be the best data to analyze the gold price, because the model doesn't fully capture the data's behavior, and there are errors, inconsistency with a missed time trend, and the data might have outlier or isn't perfectly bell-shaped, which might indicate that the normal distribution might not be the best choice for this analysis.
For the ARIMA, we evaluated several ARIMA models with d equals to 0 or without differencing required, as we have differenced in the beginning stages. The ARIMA 100 model was selected as it had the lowest AIC score of 2,765. Here are some key observations. All models showed similar log likelihoods, around 1379, indicating minimal differences in fit quality. Adding more parameters such as increasing in P or Q values wouldn't significantly improve the model. The simplicity of AR1 makes it preferable here, parsimony principle. Next would be the Jung box text result. Here we can see that the p-value is bigger than 0.05, which confirms no significant autocorrelations remain in the residuals. For the model summary, it shows a degree of freedom of 262, white noise variance of 2042, and a consistent AIC scores with our selection of negative AR1 coefficient of negative 0.144 which suggests that a mean reverting behavior in the data. This shows that both constant 6.83 and AR terms are statistically significant, showing that P is smaller than 0.05. Here we have some ACF and PACF plots, which shows no spikes outside the confidence limits. This visual confirmation supports the Zhang box text result. The residual analysis indicates that there are no remaining autocorrelation patterns, and the model has adequately captured the time series structure and a good model fit for the data. Here are some residual plots for C8. The key takeaways are that the residuals appear normally distributed, and there are no evidence of heteroscedasticity and no time-dependent patterns in the residuals. Lastly, here are the time series plot with the prediction. While the model fits historical data well, it has a limited predictive power for future values. The wide interval suggests high uncertainty in forecast. This may indicate either that the fundamental limitations of ARIMA for this dataset or the need of additional explanatory variables. The conclusion is that the ARIMA 100 model is statistically adequate for describing weekly gold price movements, showing mean reverting behavior. However, its limited predictive power suggests that for practical trading or investment decisions, a more sophisticated model or additional economic variables may be needed to improve forecast accuracy.
Thank you.